Good morning, everyone. I'm glad that you're watching the video. Hope that you're having a great morning. And what we're going to do today is we're going to talk about doing double integrals but using polar coordinates. And suppose we want to, evaluate a double integral where R is one of the regions shown below. So our region R is a circular region. So basically what we want to do here is we want to, anytime we're given, a region that looks circular, we're going to change into polar coordinates. And I know that you were probably told you'll never use polar coordinates again, but no, you will use polar coordinates. Not only here, we'll do it again in next week. And even next week, we're going to talk about spherical coordinates. And cylindrical coordinates, and they're going to be based off of polar coordinates. But today here we're just going to talk about polar coordinates. It's what it really is doing is making your life a lot easier when we're trying to evaluate regions that are circular. I mean, this makes work very easy. The hard part is just making sure that and it's really not that hard, is making sure that you're using the correct, that you're just converting to polar coordinates correctly. So here we have a region, and our region is going to be defined by, now this is not big enough, so I'm just going to put it up here, like that little box that I have is not big enough to write it. So the region here, and if we talk about polar coordinates, we're going to convert this region to r and theta, where r is the radius and theta is that angle measure. So r, theta. And our region is not going to be that hard. When we're talking about radius, what's the radius from the center of the circle? Well, the radius is going to be, it looks like 1, so r is going to be between 0 and 1, and our theta measure is going to be, we're going from that terminal side, so the terminal side is the x axis, and then we're rotating this, and we're doing a full rotation, and because we're doing a full rotation, it's going to be between 0 and 2 pi. And so that's our region. Now, what if we have kind of a washer where, remember the disc method, the washer method. On the left, we have a disc. On the right, we have a washer. Well, that's not going to be more difficult. We're just going to we're still going to do the region of our radius and theta. But now r is going to be between, instead of, 0 and, whatever our radius is. In this case, our radius is 1. In this case, our radius is 2. All right, remember, it's r squared. So our radius is going to be between 1 and 2. And in this case, we're doing a semicircle. We're not going all the way. Again, we always go counterclockwise. All right. I mean, you could go clockwise, but you're making it a lot more difficult for yourself. So that's going to be a distance of pi for theta. So we start at 0. No, write my thetas correctly, and we're going to pi. All right, and so that's, we're changing this region now, and we're changing everything to polar coordinates. And again, hopefully you're going to see, oh, that's not that hard. The best thing to do is to draw the region, because then you'll see, how to change everything. All right, so what we're going to do now is just talk about all the different conversions for polar coordinates. So anytime we're wanting to change to r or theta, and we have x and y, we're going to go ahead and use this notation. So r squared equals x squared plus y squared, equation of a circle. X equals r cosine theta, and then y equals r sine theta. Again, these two are given by Pythagorean identities for a right triangle. All right, now, one other one I want to add that's not here, that I'm pretty sure that you learned this in Calc 2, is if we do tangent theta is just going to be y over x. So just add that there, because it could come up, and I want you to go ahead and just do that conversion. It's not difficult, but I mean, it could save you some work if you do see y over x. You don't have to write, r sine theta over r cosine theta. All right, so let's look at kind of the region that we have. So these regions are special cases of polar rectangles, and so our region, again, is going to be defined by r and theta And when we talk about r is going to be the distance, from the inside radius to the outside radius. So it's going to be that distance. And then theta is always going to be counterclockwise, so it's going to be that, don't want a straight line. It's going to be about going from kind of like right to left when we go the counterclockwise direction. All right, so basically what I'm going to do is I'm going to kind of show you how we can find, our delta A, our change in our area. And so one thing that I want you to know is that the area of a sector, because this is what this whole thing is. This part right here is just a sector. And we know how to find the area of the sector. To find the area of the sector is just 1/2 r squared theta. All right, that was something that you were taught in geometry, and trigonometry kept it there in your mind. I don't know if you just remembered the area of a sector formula right off the top of your head. This probably was used in some of your physics classes. But so what we can determine is if we have delta A, and now they use two different r's. They have r sub I and r sub I minus 1. I'm going to go ahead and say, hey, this is r sub 2 and this is r sub 1. All right, so r sub 2 is pretty much the radius that goes all the way to the edge, and then r sub 1 is this radius right there. All right, that way it's just easier to know instead of having to write r sub I and r sub I minus 1. All right, so our area is just going to be, if we wanted to find this area, we'd find the area of the larger sector minus the area of that smaller sector, and we would get the area of our sector here, because this is a disk, because this space right here is empty. And so we would take the area of the whole thing, and so I would get 1/2 r squared, or I'll say r sub 2 squared times theta. Now, because theta is changing, it's going to be this change in theta. So this change from, our theta, because that's changing, again, we want to, define this throughout, all circumstances. We're going to say delta theta, right? That change in theta. Minus, now we got to take the area of the smaller sector, and we're going to have 1/2 r sub 1 squared delta theta. All right, and then what you can see is we can, we're math people. I can simplify this. I can pull out a 1/2. So we pull out a 1/2, we get r sub 2 squared minus r sub 1 squared times our change in theta. Well, I can change this because this right here is a difference of squares. And so I can write 1/2 r sub 2 plus r sub 1 times r sub 2 minus r sub 1 delta theta. And then I'm going to change it one more time. Well, when we know that, delta is just the change in your, whatever, I guess, variables that you have. Well, here we have that change. R sub 2 minus r sub 1 is going to be that change. So I can go ahead and rewrite r sub 2 minus r sub 1 as delta r, and then have delta theta. Now, the only other thing right here is that we have the sum of our two radiuses divided by 2. Or what we can think of is we have some value in between. More than likely, we have the midpoint. All right, and so we could say, this represents kind of the midpoint. Whoa, it's not in the middle. This thing is a little off. So we have like the midpoint of each of these little rectangles. And so this is just an r, and we'll denote that r by saying r sub I dot. All right, and that's where this is coming from. All right. And so when we're doing, when we're changing to polar coordinates, we cannot forget this little r. So this is going to, be added into our integral, is this value here for this r. So now let's go ahead and look at, how we're going to do like the summation of this when we're talking about integration. I hate having to write it this way because this is really what we're going to be working on. But again, so we're going to do the summation m I1 and j equals 1, and then of our function. Again, remember, it used to be of x and y. Well, x is now r cosine theta, y sine theta. And so let me go ahead and get rid of that. I'll just keep that there. So we have f of r sub I dot cosine theta times r sine theta. But now our delta A is going to be r change in theta, and again we'll just put the i's here, i's and dots. We don't need to do that. Just keep it there. All right.